All right, then let's start. I forgot your title. Quotient inductive type, something containers?
Something with containers and quotient inductive types and categorified containers.
Okay.
Yeah. Okay. Hi. Good morning. Yes. So I wanted just I didn't want to present any new results, but I made an observation which I thought may be interesting, and I'd like to explain it. So let me first give a bit of background. So what are containers? They are also called polynomial functors. And my definition is this: if I have a set S and a family of sets indexed over S, then I can make a container, which I write like this, P. And it can be interpreted as a functor from set to set. So here I write this to represent functors, and I'm saying S triangle P of A is just sigma S in S, PS to X. Now it's clearly it's a functor. And when we developed this theory of container, our main idea was to have a general representation of strictly positive types. And indeed, container are the algebras of W type. So, or not the algebras, the functor, the signature functor of W types. So the initial algebra of a container is just a tree, and that's the representation of strictly positive data types. And one example, simple example, is lists. So lists we can represent the shapes are the lengths of the list, and for every length we have a finite set of type n of positions. So that's the basic idea. Okay, let me tell you that this is a functor. It's actually a two-category. So we have a morphism between containers. So if I have two containers, then a morphism is given by a function f on the shapes, and then a function g which sort of goes the other way around, goes from Q f s to P of s. And it's easy to see that every container morphism, it gives rise to a natural transformation. So natural transformation I write as an end from S triangle P x to T triangle Q of X, so natural transformation. But actually it goes both ways. This is an isomorphism, which is one of the first things to realize if you look at the category of container, that actually these represent all the natural transformations between container, giving you a small representation of natural transformations, which is quite useful. So that's one of the things I wanted to say. And the other observation about containers is that you can derive an operation of derivative. So if you have a container, then the derivative of the container is the data type with one hole. So that is actually a generalization of the formula for derivatives of polynomials. I mean, all the polynomial functors. So the shapes are now a shape together with a chosen position, and the positions are P of S with P removed. So what do I mean by this? I mean, it's a P prime in PS such that P prime is not equal to P. So I remove one position. And it's maybe interesting to note what is the derivative of lists. what's a list with a hole? Now, a list with a hole is two lists, namely everything to the left and everything to the right. So this notion of derivatives just follows the usual laws of calculus derivatives in calculus, and it's interesting that you can, just using the chain rule, you can derive this equation. It's quite fun to do this. So it's the chain rule with fixed points. Okay. So let me move on. Oh, I have filled already one blackboard. How did I manage this? But I was supposed to write large, no? Does this work? Can I do this? Okay. So now let's move on. So this is the classical theory of containers. Now I want to talk about QITs, quotient inductive types, which are set truncated hits. And here's one example. I've mentioned lists before, so let me do a bit of whiteboard ACTA. So I want to define the multisets over a set A. And I mean, I'm not going to repeat the constructors for lists. So you have cons and you have nil. But now you get an equation which I call swap, which tells you that A cons B cons X's is the same as B cons A cons X's. So you can swap any two elements, and since you can repeat this, you really get multisets. The order of this list doesn't matter. The question is now, can we represent this as a container, data types like this? And here, very helpful, there was the MSc thesis by Håkan Gilderud. I think it was 2011, and was entitled Symmetric Containers. So I know about this because I was the external examiner, and I was very impressed. Where's Håkan? Ah, there. I was very impressed. I think it was the best MSc thesis I've ever seen. It was something which other people would have submitted as a PhD. So that was really great stuff. Now, this was pre-HoTT, but I think in the language of HoTT, we can express what is a symmetric container by just replacing this by a groupoid or one type. But now, if you want to have a functor on sets, I have to truncate this. So that's a bit ugly, because in particular, this thing goes down the drain if I do this. But let me get away. So this is a symmetric container. We have a shape is now a groupoid or one type, and it's easy to see. Do I have time? Yeah. That this can be represented now as a container where we take the symmetry groups of size n as a groupoid. Or let me define this in ACTA. So I embed all the natural numbers, and then I have I just met EQ. Then I say if fin of M is equal, if I have univalence, otherwise I have to write isomorphic, then eta of M equals eta of N. Okay. Okay, and what are the positions? The positions of eta of N is fin N, and the positions of EQ of P is just P. So that's one way to define this groupoid of symmetry groups in HoTT or cubical ACTA. Now it's easy to see, or I tell you, maybe you can see it, that maybe I should number them, because I had SP now. That the multisets are exactly the groupoid or symmetric container of for multisets, and yeah, with this S and P. Now, when Håkan introduced symmetric containers, he did this because he was interested in antiderivatives. And actually, one result is that there is an antiderivative of lists, which are the cycles. So instead of symmetry group, I use a translation group, and the derivative of cycles is list. But the multisets play the role of the exponential function. So the derivative of MS is MS. So that's interesting to note. Now we may wonder, can we represent all interesting quotient inductive type using symmetric containers? And that's maybe the main point I wanted to tell you. So what are the counterexamples? So the first one is a well-known truncation, I mean propositional truncation, which goes from set to prop. Now, okay, I have time. So here's a little argument why this cannot be. So we know that for 1, the truncation is 1. And that entails that the shapes of any such container must be 1, meaning it's just a representable functor. But if it's a representable functor, okay, we know that 2 is also 1, and that implies that P must be 0, right? Because, yeah, 2 to the 0 is 1, but there's no other choice. So P must be 0, but, sorry? It's 0 to the 2, yeah, thank you. Okay. Yeah, I'm putting in these little mistakes so then you know that the audience is still following you, you know, it's a method, you know, I mean. Okay, but now 0 is 1, 0 is 0, which is not, what is this? Yeah, which is not 1, which is not, what is not 0 arrow 0, which is 1, right? Okay, so 0 is not equal to 1, that's always a problem. Okay, so we have this, so now let me give you another counterexample. It's finite sets. So finite sets we get by modifying our multisets. Oh, I didn't leave space here. By adding another constructor, what do you say, copy or something, which says that A cons x's is equal to A cons x's. So you can collapse several A's. Now you can also show that that this cannot be a symmetric container. You get because if you apply a function which identifies elements and the shape is changing, and that's something which you cannot do with symmetric containers. Okay. So now, what is? I didn't think I would run out of. Is there a problem? My micro is not. Oh, okay. Oh, I have some space here. Maybe I go here, because I don't want to start a new whiteboard. So finally, a way to at least address these counterexamples is another notion which was introduced by Håkan, namely categorified containers, which done by him for cut containers. categorified containers is another change here. We replace groupoids by categories. And then obviously, maybe we should be more explicit that this is actually a functor from this category to sets. And what do we do here? So here, the meaning, or let me do this here, the meaning of a categorified container is now at A, is now coend, or colimit in this case. Okay. So it's a coend. So let me just quickly write down what this means. So the elements are S, F, so it's like a sigma type. And if I have a phi amorphism in S from S0 to S1, then S0 F composed with P, oh, I'm running out of space here, is S1, F. So I'm just spelling out what this coend is, or what this colimit is in this case. So it's just the obvious thing. And now we can fix these counterexamples. So in the case of propositional truncation, we can present a cut container with the following category. We have two objects, 0, 1, and two morphisms, 0, 2. And the morphisms I call 0, 1. And what do I mean? I mean what they say. So this is S, and P, no, that's 1, sorry. So P sends 1 to the 1 element sets, 2 to the 2 element sets, and 0 and 1 to true and false. And now we can model so eta, which goes from A to meaning of A, to truncation of A. So eta of A is just 1, comma, and then the function, the constant function, which is A. But we can show that eta of A, which is 1, comma, lambda A, is the same as 2 lambda B if B, then A, else B. And how do we do this? We use this equation there with phi equals 1, which is true, so it gets A. And that is the same as 1, comma, constant function B, which is eta of B. And since we are actually truncated, this is enough to show that this is propositional truncation. All the higher equalities are truncated. Okay, so what do we do for the finite sets? So finite sets so the S is the category whose objects are natural numbers, and the morphisms are just the functions from fin m to fin n, which are surjections. And so what's the idea? Now, if I have a finite set like A, B, and another finite set A, B, B in this list representation, then we can using surjections to show that this is equal to this and this is equal to this. So we can always collapse elements, but we can never get rid of them. So this way we get a representation of finite sets. Okay. So what's the conclusion? Where do I put the conclusions now? Okay. So here, so one question is, so using these categorified containers, I also give rise to a new W type, and I call it QW type. And the question is this a nice short version of a universal inductive type constructor for quits? I don't know yet. I don't have a general scheme how to reduce them. And if we replace here categories with higher categories, so the whole message is actually do directed things. If your symmetric things don't work, then go directed. And it seems that go directed here at least helps in some cases. So if we go higher directed, maybe we get something which represents hits. We can represent generally hits more general in a short form. And one question which I have discussed with Håkan is also, can we extend the derivative operation for categorical containers, so categorified containers? Because Håkan, in a way, he first introduced categorified containers, but then he said, okay, hang on, we cannot derive derivatives. That's what I really want to study. That doesn't work. But maybe we should revisit this. It would be interesting if we can extend this construction. Okay, thank you.
Other questions? Yeah, Andreas. Yeah.
I was puzzled for most of the talk about the derivative of list, that it's list times list.
Yeah.
Am I missing it, or?
No, I mean, okay, first we can do it algebraically, but it would take a moment, right? You're using the chain rule, you can prove this. But actually there's an intuitive version. If you have a list, right? Like a list, elements, and you make a hole in, what you get? Two lists, yeah? This, by the way, also explains why the antiderivative of lists are the cycles, because if you have a cycle and you cut it in one point, you get a list, right?
Other questions? Daniel? Yeah.
Maybe, what are some of the difficulties for extending this derivative to these categorified containers?
Yeah, so because I also, it was Håkan who reminded me what the problem was. Once we have the subtraction operation, we cannot extend, this doesn't give rise to a functor. Even if P is a functor, then after subtracting this, that's not the counterexample where this is not a functor. So we have to adjust things. However, I would think that the derivative of finite sets should also be finite sets. So, I mean, in this case, there would be more than one fixed point of derivatives. There is a universal property defining derivatives. So basically, if you have morphisms into a derivative, so let's say in cont, then that's the same as okay, actually linear morphisms. So these are, let me write like this. The linear morphisms are the Cartesian one, where the pullbacks, where the naturality squares are pullbacks, and this are the ones where the positions are preserved as a morphism. The morphisms on positions here is an isomorphism. Yeah, so you don't drop or copy anything, and then we can just define the derivatives as h times, which is not, it's not the product in this category. Right? It's the product in the ordinary category, so the Cartesian product, which is now a tensor product, into F. So basically, we send this I somewhere and make a whole. And this is a sort of definition of derivatives not based on the representation, but based on its universal properties. And we can now look whether we can find something like this in the category of categorified containers. Maybe not for all of them, but at least for some.
Okay. Then let's thank Thorsten again.